Okay, so I want to talk about a variant of the double shuffle relations for multiple zeta values and a connection to modular forms, or more precisely to quasi-modular forms. So this audience of this seminar is quite mixed. So I will really talk about the basics of all the objects, and I hope I actually come to the title of my talk. So either it will be a variant of the double shuffle relations or a motivation for a variant of the double shuffle relations. So this talk is based on two joint projects with Annika Burmester from Hamburg. And the second project is with Ulf Kühn and Niels Mattes. So Ulf Kühn in Hamburg and Niels Mattes in Oxford. And both projects are still a work in progress. Okay, so let's start. But before I start, I want to do some advertisement. So last semester, in the first Corona semester, I gave an online lecture on multiple zeta values and modular forms. So if you're interested in this, there's on my homepage, you can find lecture videos on YouTube and also lecture notes where I explain in more detail some results I present today. Okay, so what I want to explain today is the following table. So this table has 2 columns and 3 rows. And the first column corresponds to numbers, and the second column corresponds to functions, or in our case, more precisely, to Q-series. And the first row corresponds to single objects, and you will see what I mean by this. And then the second row will correspond to multiple objects. And in the last row, we can see their relations. So what are the entries of the first column? So the single object, the numbers we are interested in are Riemann zeta values. And the multiple versions, which maybe already appeared in some talks before in this seminar, are multiple zeta values. And then maybe some of you also saw that these numbers satisfy certain relations, which are called double shuffle relations. And this I will explain in detail later, but for the main point is that, for example, the product of 2 Riemann zeta values can be written in terms of these multiple zeta values in 2 different ways. And these double shuffle relations can also be interpreted in 2 different ways. So I can either write them down like this, but I can also write them down by using generating function or generating series. So somehow there are 2 different points of views. So somehow the object point of view, where I write down the product of these objects and write it in terms of these objects, or I consider their generating series, and then I will have some functional equation for the generating series. And if I consider the coefficients of these functional equations, I will get this here. Okay, so now let's move to the second column, to the functions. So what are the single objects in this column? So this will be the Eisenstein series. And the connection of these 2 objects, Riemann zeta value and Eisenstein series, are given by the fact that the Riemann zeta value appears as a constant term in the Fourier expansion of these Eisenstein series. And these Eisenstein series are the building blocks of modular forms for the full modular group. And they are also the building blocks for the so-called quasi-modular forms. So if you see this picture now, the natural question is, what are the entries of these empty boxes here? So what is the multiple version of Eisenstein series? And this question was first considered by Gangel, Kanike, and Sage. So Gangel is here, so I'm really happy about this. And they considered the case R equals 2, so the double case, and they introduced so-called double Eisenstein series. But then there's, of course, a natural generalization by so-called multiple Eisenstein series, which I will also define later in more detail. But you can think of them being the multiple version of these Eisenstein series, which are also given by, so they are also some functions, but they also have a Fourier expansion. And the constant term of their Fourier expansion is then given by these multiple zeta values. And now the big question, or the motivation for this talk, is this part here. So this is what I want to explain at the end. And so the goal of this talk is to somehow propose some kind of functional equations here for the generating series of roughly speaking, these multiple Eisenstein series. But we will see that we are not just interested in Eisenstein series, but also their derivatives, and even more than this. So this will be the goal of this talk. And so the plan of this talk is that I will start by going into detail about this first column here. So I assume that some of you maybe don't know the definition of multiple zeta values and these double shuffle relations. So I will explain this in the first part. Then in the second part, I will recall some basic facts about modular forms, and in particular Eisenstein series. And at the end of this section, I will also, besides this naive connection here that the Riemann zeta value is the constant term, I will also explain in a deeper result on the connection between multiple zeta values and these objects, which is given by the so-called Broadhurst-Kreimer conjecture. And then in the third part, I want to somehow explain one part of this Broadhurst-Kreimer conjecture by using these multiple Eisenstein series. And then at the end, I want to talk about these double shuffle relations for these functions. Okay, so let's start. Of course, first, let's start with the definition of multiple zeta values. So if I have natural numbers, k1 up to kr, where the first one is greater or equal to 2 and the rest is greater or equal to 1, then the multiple zeta value is defined by this iterated sum here. And this number r, so the number of k's, is called the depth, and the sum of these k's is called the weight. And then we can consider the Q vector space spanned by all these real numbers, which we denote by z. And as we will see on the next slide, the product of two of these multiple zeta values is again expressible as a linear combination of multiple zeta values. Therefore, this space Z is a Q algebra. And there we also consider for a fixed weight K, the subvector space spanned by all these multiple zeta values of weight K. So besides this representation as an iterated sum, we can also write multiple zeta values in terms of iterated integrals. And I will not write this down in general. I will just give this one example. So for example, this double zeta value, zeta 2, 3, is of weight 5. And this can be written as this iterated integral of length 5, where I have two different differential forms, this dt over 1 minus t and this dt over t. And you see for each index, I have some block starting with dt over dt, and then end with dt over 1 minus t. So this here corresponds to the index 3, and this here corresponds to the index 2. And to go from there to there, you just expand this here as a geometric series, and then you will see that this is actually true. Okay, so these two representations then give us two different expressions for the product of these numbers. So the first one is called the harmonic product, or sometimes also called the Staffel product. And I saw in some talks that there were, so I saw on the seminar page there were some talks on quasi-shuffle products. And this harmonic product is an example of a so-called quasi-shuffle product. So this comes from the definition as this iterated sum. So if I take the product of two Riemann zeta values, which by definition is given by this here, then I can consider these three cases that this m is greater than this n. So I get this part here, or this n is greater than this m, then I get this part here. Or these two numbers are the same, then I get this part here, and the exponents of these, they add up. And then you see that this here is exactly the definition of the double zeta value, zeta k1, k2. And this is the definition of zeta k2, k1. And this is just the Riemann zeta value of weight k1 plus k2. And so therefore, we can write the product as a linear combination of multiple zeta values. And you can also see that this works in general. If I have an iterated sum here, an iterated sum of arbitrary depths, then this combinatorics works, and I can write this as a linear combination of multiple zeta values. And the shuffle product, which comes from the expression as iterated integrals, can be written down like this. And so we saw on the slide before that these iterated integrals are given by these integrals with two different differential forms. And we can think of this as being two types of cards. And then if I multiply two multiple zeta values, I just take these two decks of cards and shuffle them together. And if I rewrite this again as an iterated integral, I can also see that the product of two multiple zeta values is again a linear combination of multiple zeta values. So therefore, these binomial coefficients here can be interpreted in some combinatorial way by shuffling two decks of cards with two different types of cards. Okay, so therefore, we have two expressions for the product, and therefore this gives us relations among these numbers. So for example, this is what you saw in this table, that zeta 2 times zeta 3 by this harmonic product is expressible like this. And using the shuffled product, we get this formula here. And because they are the same, we get this linear relation here between these numbers. And this gives a big family of linear relations, but it turns out that this is actually not enough to get all relations. So for example, it was already shown by Euler that, for example, zeta 2, 1, which by definition is this sum here, equals zeta 3, which by definition is this. And this is a non-trivial relation. But also this cannot follow from this here, because to get something in weight 3, I would need to multiply zeta 2 with zeta 1, but zeta 1 is not defined. But one can show that one can actually make sense of this here with divergent sums. So one can show that I'm allowed to multiply with zeta 1, whatever this means. And then here on both sides, I have some divergent terms. But then one can show if one subtracts these both sides, these divergent term cancels out, and the relation you get is does actually hold. And this is a way to prove that that zeta 2, 1 equals zeta 3. And these regularized double shuffle relations are also called extended double shuffle relations. And then one of the holy grail in this field is that we conjecture that these extended double shuffle relations actually give all relations among multiple zeta values. And in particular, because these extended double shuffle relations just give relations among multiple zeta values of the same weight, we also expect that this space Z is graded by weight, meaning there are no relations among different weight multiple zeta values, and therefore this space Z is the direct sum of these spaces Zk. And this is now just a remark and not important for this talk, but besides these extended double shuffle relations, there are a lot of different families of relations among multiple zeta values where we expect that these families give all relations, but not for all of them. It's clear that these families are equivalent to this extended double shuffle relations. So for example, in my lecture notes on this topic, you can find an overview of different families of linear relations. So here I mentioned these extended double shuffle relations, but there are various families. For example, there's the so-called associator relations, which conjecturally also give all relations. And there are also these so-called confluence relations and so on. But for example, here, between associator relations and these extended double shuffle relations, we don't know if they are equivalent, but we know that the associator relations imply the extended double shuffle relations, but the other direction is not known. And this direction here was shown by Fruscio, who's also here today in the audience. Okay, but now another conjecture, which is due to Zagier, is on the dimension of the space Zk. So Zk, recall, was a space spanned by all multiple zeta values of weight k. And he conjectures that the dimension in weight k is given by these numbers dk, and this dk is defined as a coefficient of this rational function here. So, but one can also write this in a different way. One could define them recursively. One could say that giving certain start values, that you have this recursion here similar to the Fibonacci numbers, but with one more shift, because this follows by this expression here. And the conjecture is that the dimension of this Zk is given by these numbers. So for example, here we have a table of these dks. So for example, here in weight 3, the conjecture is that the dimension is 1. And there are two multiple zeta values in weight 3, namely zeta 2, 1 and zeta 3. But we already saw they are the same. So at least in this case, we can prove that the dimension is 1. And here in weight 5, the conjecture dimension is 2, and we have 8 possible multiple zeta values. So we expect that there are 6 independent relations. But even though we can give an upper bound by just proving some relations, we actually cannot prove lower bounds. So we can actually not prove that this is 2. And in fact, we can not prove for any weight that the lower bound is better than 1. But what we can prove is actually for every weight, the upper bound, which was independently proved by Terasoma and Delin-Goncharov. So they showed that these numbers dk actually give an upper bound of the dimension zk by using some geometric methods. Okay. So this was section 1. So this was a rough overview of multiple zeta waves, but later we will come back. So we stated the conjecture of Zagi, and then later we'll state a refined conjecture due to Broadhurst and Kreimer, which involves Cusp forms. But for this, I will first recall some basic facts on modular forms. So let H be the complex upper half plane, so all complex numbers with a positive imaginary part. Then a holomorphic function in the upper half plane is called a modular form of weight k if it satisfies 3 conditions. So the first condition is that it's 1 periodic. Then the second condition is that it satisfies this functional equation here. And then the third condition is that it can be expressed as a Fourier, that it has a Fourier expansion of this form here, where the important part here is that this sum starts at 0. So from this 1 periodic property here, we can already get that we have an expression like this, but we don't know if this starts here at 0. So what this basically also means is that if I have the upper half plane here, this statement is equivalent to saying that if I go to I infinity here, that these functions are bounded. In other words, one can also say that, this is usually called that these functions are holomorphic at infinity, because this function here as a function in Q in the unit disk can be extended holomorphically into 0. Okay, so this is the definition of a modular form. Even though I cheated a little bit, usually you define an action of SO2Z on the upper half plane by Möbius transformation and then say that these modular forms satisfy certain conditions. But one can show that one actually just needs to check these 2 conditions yes, to define a modular form. So by MK, we now define, we denote the space of modular forms of weight K. And in this space, we have an important subspace, which is the space of Cusp forms, which are all modular forms of weight K, where the Fourier expansion starts at 1. So in other words, that the constant term of this Fourier expansion is 0. Or in other words, those functions which vanish if you go to I infinity. And so what are examples for a modular form besides the trivial 0 function? So the first non-trivial examples are Eisenstein series. So if you have an even number k greater or equal to 4, you define the Eisenstein series of weight k as a function in the upper half plane. So this tau here is in the upper half plane. And you define this by this sum here, where you sum over all tuples m and m, which are both not 0. And then you take this term here. So in other words, you take the sum over all lattice points in the complex plane except 0, and you take this sum here. And then one can show that the Fourier expansion of this Eisenstein series is given by like this here. So for example, for the case m equals 0, we see that we get exactly this term here, because for m equals 0, we just have the sum over all non-zero n, and so therefore we have twice the Riemann zeta value, and because of this factor 1/2 here, we get zeta k. And then the rest of the Fourier expansion is given by these divisor sums, which are given by the sums over all divisors of the number n. But this I will also explain later in more detail. And then a basic fact about modular forms is that these Eisenstein series are the building blocks of all modular forms. And even, so the first statement is that they are actually modular forms of weight k. And then the statement is that we actually just need G4 and G6. So every modular form is a polynomial in G4 and G6. And so this is now defined for k greater or equal to 4, because for example, for k equals 2, this sum is not absolutely convergent. But this expression here makes sense also for k equals 2. And therefore, we can consider the following. So first of all, modular forms are holomorphic functions in the upper half plane. So we can ask what happens if I take the derivative of a modular form. Is it again modular? And the straight answer is that this is not the case. So you can check easily that the derivative is not a modular form. But one can also show that the only thing missing somehow is the Eisenstein series of weight 2, which we now define by this Fourier expansion and not by this sum over lattice points. So this here is just the formula of the slide before, with just plugging 2 into plugging 2 in for k, and then we define the space of quasi-modular forms as a polynomial ring in G2, G4, and G6. And then the basic fact for this space is that this space is closed under taking the derivative. So this is closed under d dd tau. And also it is the smallest ring which contains the ring of modular forms and which is closed. And by smallest, I mean if there's another ring which contains the ring of modular forms and which is closed under d dd tau, then this also contains the ring of quasi-modular forms. Okay, and now, so we also defined Cusp forms. So these were modular forms where the constant term vanishes. And so the first example for a Cusp form is the delta function, which can be defined by this product here. But I said before that G4 and G6 are the building blocks of modular forms. So you can also write this as some factor times G4 cube plus some factor times G6 squared. And then the statement is here that these are the building blocks for Cusp form, meaning that any other Cusp form can be written as a product of this delta function times a modular form, or more precisely that multiplying with delta gives an isomorphism from the space of modular forms of weight k to the Cusp forms of weight k plus 12. And for this, one just needs to show that delta doesn't vanish in the upper half plane, which can be derived from this product expansion here. And then if I have a Cusp form, I can divide this Cusp form by delta and then can show that this gives me a modular form. And why am I stating this here? Because what I want to explain is the generating series of the dimension of Cusp forms. So by this first statement here, the generating series of the dimension of Cusp forms is just the generating series of the dimension of modular forms times the factor x to the 12, because this follows directly from here that the dimension is just shifted by 12. And by the statement that all modular forms, or the space of all modular forms, is a polynomial ring in G4 and G6. And then one can also show G4 and G6 are algebraically independent. And with this one can then show that that generating series of the dimension of modular forms is given by this term here. Because if you multiply this out here, you just get exactly the number of polynomials in G4 and G6. And then we still have this factor here. Okay, so this you should remember that the dimension of Cusp forms gives me this factor here. And because what I want to do now, I want to go back to multiple zeta values and state this conjecture to Broadhurst and Kreimer, which involves exactly this function here. And the statement, if you maybe see it the first time, looks a little bit confusing, but let's do it slowly and explain every part here. So we had this dimension conjecture due to Zagi, which gives the a conjecture for the generating series of the dimension of multiple zeta values of weight k. But now, instead of just considering the weight, we also want to consider the depth. And the depth is a filtration on the space of multiple zeta values. And by this here, I denote now the associated graded part. And what this just means is that I consider the weight k multiple zeta values of depths r modulo lower depths multiple zeta values. So for example, what is the graded part in depth 2 of Z3? Well, there's one multiple zeta values of weight 3 and depth 2, which is zeta 21. But we learned zeta 21 equals zeta 3, and zeta 3 is depth 1. So in this case, this space here is just the trivial space, because every multiple zeta value of depth 2 and weight 3 modulo lower weight is vanishes. And then the conjecture by Broadhurst and Kreimer gives a conjecture for the generating series now in two variables, the x for the weight and the y for the depth. And the statement is that this is given by this fancy looking rational function here. And what are the building blocks of this rational function? So there are three things here, this O and E. And this E is just this function here. And if you write this out, what this just is just somehow it counts the even numbers. And O somehow gives the odd numbers without 1. Or you can also think of these, give all the single zetas of odd weight and even weight. And this here we saw on the slide before, this is exactly, this counts Cusp forms. Because this here gives the generating series of the dimension of Cusp forms. So therefore, if we write this function here out, what we get is this. So here the constant term just corresponds to which we didn't define. The multiple zeta value of depth 0 is we define to be 1, and there's just this. But here in depth 1, what we have is the sum of EX and OX, which makes sense because we expect that these single Riemann zeta values are all non-rational. So if you would divide out lower depths, meaning rational numbers, then we don't kill anything. So therefore, for each weight, we have exactly one Riemann zeta value, and therefore the dimension is exactly given by this. And here we also see this O starts at 3 and not at 1 because we don't have zeta 1. So this is what we expect, but still also this part is not known because we don't know if, for example, zeta 5 is not rational or not. If zeta 5 would be rational, then we wouldn't have this term here. And then for depth 2, we have this part here. And so there we can distinguish between even and odd weight. So for odd weight, the only possible contribution is here EX times OX. So even plus odd is odd. So here we actually expect that this space is generated by the product of even zetas times odd zetas. But the more interesting part is this here. For even weight, we have this OX times OX. So somehow pairs odd, odd. And then there's a minus sign here, minus SX. So the interpretation is that in even weight, in depth 2, we somehow, as generators, we have something which is counted by counting all tuples odd, odd, adding up to the weight, minus the number of Cusp form, meaning Cusp form gives a relation among zeta values. And this term here, I want to explain in the following by using a multiple Eisenstein series. Okay, So let's go now to part 3, where I talk about multiple Eisenstein series. And these are, as we saw on the table at the beginning, can be seen as a multiple version of Eisenstein series. And therefore, to define them, we first define some order on a lattice. And then instead of taking the sum over all lattice points, we will take an ordered sum over lattice points. And this definition is due to Gangel, Kaneke, and Sagi. So they use this to define a double Eisenstein series. So let lambda 1 and lambda 2 be 2 points in the lattice z tau plus z. And we say that lambda 1 is greater than lambda 2 if the difference is in the set P, where by the set P, I mean this set here, which are all lattice points in the upper half plane and all lattice points on the positive real axis. So what this just says is that if I have a point here, let's say here I have lambda 2, then lambda 2 is smaller than all lattice points which are above or on the right of lambda 2. So for example here, if there's lambda 1, then this lambda 1 is greater than lambda 2. But also this lambda 1 or this lambda 1 and so on. Okay, so this gives a total order on the lattice z tau plus z. And this we can use to define now multiple Eisenstein series, which we denote by this here, gk1 up to kr. And now we need to be a little bit more careful than in the definition of multiple zeta values. So they were defined for all integers where the first one needed to be, all positive integers where the first needed to be greater or equal to 2. But here, for convergence reasons, we need this k1 to be greater or equal to 3, and the rest to be greater or equal to 2. And then we just copy the definition of multiple zeta values and replace all positive integers by positive lattice points, which are ordered by this order I defined on the slide before. And because this is also defined by this ordered sum, we saw at the beginning that this harmonic product, I mean, we didn't care what we sum up. We just cared about this. If I multiply 2 of them, that I can distinguish these different cases. And therefore, if I multiply, for example, G4 with G3, I can do the same argument and also get that this harmonic product formula holds for these multiple Eisenstein series. But of course, this just makes sense in the case when K1 is greater or equal to 3 and the rest are greater or equal to 2. Okay. And so now I want to go to the Fourier expansion of multiple Eisenstein series. And to do this, I first want to recall how we actually calculate the Fourier expansion of classical Eisenstein series. And also, let me go back to the definition here. So for the case R equals 1, we see that this definition here now extends the definition of our Eisenstein series we've seen before a little bit, because in the first definition of Eisenstein series, I defined this gk to be the sum over all lattice points except for 0. Therefore, if I take k to be an odd integer, then these positive and negative parts would cancel out. But here in the case when r equals 1, I will just take 1/2 of this lattice, and therefore this sum does not vanish in the case when k is odd. So what I mean by this is that in def 1, these Eisenstein series are given by this. So now we have for all k greater or equal to 3 that we have a non-vanishing sum here. And this summation can now be split up into the lattice points in the upper half plane and the lattice points on the positive real axis, meaning the upper half plane is this m is greater than 0, and positive real axis is this part here. And as I said at the beginning, this on the part on the positive real axis gives me the zeta value, and the rest gives me this sum here. So here I just have the, I take all the sum over m, and for a fixed m, I take the sum over all n on this line here. And this, to evaluate this part here, we use a so-called Lipschitz summation formula, which states that a sum like this, where I sum over all integers n, like here, I sum over all integers n, this sum here has a Fourier expansion like this. So here this q is always e to the 2 pi I tau. And if I plug this in here, where I also replace this tau by m tau, so here I have dm, then I get exactly what we saw at the beginning, namely that the Fourier expansion of this Eisenstein series is given by this sum here. So here I sum over all positive m, which is this here, and I sum over all positive d, which is this here, and I sum up this d k minus 1 of in front of q to the md. Therefore, the coefficient of q to the n is the sum over all its divisors raised to the k minus 1 power. And the reason why I explain this in such a detail is that I want to define a multiple version now of this part here. So I will be interested in this part, which I will call gk. And I want to somehow motivate a multiple version of this object here. And then the statement later will be that the Fourier expansion of multiple Eisenstein series are a mix of multiple zeta values and the multiple version of this sum here. So what is the multiple version of this generating series here of this divisor sum? So what is the divisor? So for example, if I have the number 6, let me take blue. For example, 6, what are the divisors of 6? Well, 6 is 6, but 6 is also 3 plus 3 plus 3. So 3 is a divisor, or sorry, 6 is 3 plus 3, usually. So 3 is a divisor and also 2. So I can 2 plus 2 plus 2, or also 1 plus 1 plus 1 plus 1. So this is a stupid way to write down the divisors of 6. So I can see here 6, 3, 2, and 1. But this here are also partitions of 6. So this is partitions of 6. And these are partitions with just one different part. So what I mean by this is that, of course, there are more partitions of 6. So for example, 6 can also be written as 3 plus 1 plus 1 plus 1, or it can be written as 2 plus 2 plus 1 plus 1. Or I can also 2 plus 1 plus. Oops. Yes. And so these are also partitions of 6, but now I allow to have with 2 parts. So here in these partitions I have always 2 different parts, but there are more partitions of 6. 6 can also be written as 3 plus 2 plus 1. So these are the partitions of 6 where I have 3 parts.
What about 4 plus 1 plus 1?
Oh, thank you. Yes. And 5 plus 1. Yes. Did I miss any? Okay. So we see here, these are all the partitions of 6. And what we counted here in the, or what we summed here were the divisors. So here, divisors corresponds to partitions of 6 where I'm just allowed to have one part. And how we want to define the multiple version of this G, in depth 2, we will consider the partitions of 6 with 2 parts. In depth 3, we will consider the partitions of 6 with 3 parts. And in depth 4, there are no partitions of 6 with 4 different parts. Therefore, the coefficient of q to the power of 6 in depth 4, in this case, will be 0. And here, so what is the m and the d here? So the M could be, for example, the 6, and the D in this case is 1. And here, for example, the M could be 3 and the D is 2. So what we will have here are two different M's. So for example, here I could have M1 is 5 and M2 is 1. And the D's are, I have 1, 5 and I have 1, 1. But for example, here, M1 is 2 and M2 is 1 and D1 is 2 and D2 is 2. So I will always have some, in this case here, an ordered sum, these different parts, M1, M2, and I have some multiplicities which are not ordered. Okay, and with this interpretation, I hope now it's clear how we could generalize this sum here. And we will also get this factor here for a reason which will become clear later. So what we define now is the following sum. So for some integers k1 to kr, we define this multiple g, k1 to kr, by taking exactly this sum here, where the number here is r. And so here, the exponent of q is exactly our the number we consider the partition. So we have different parts here, M1 to MR, and these are just the multiplicities. So if I sum this up like this, then this here is exactly the number where we consider the partitions. And we take these parts, the multiplicities, and raise them to the powers of these k's. So for r equals 1, this is exactly what we had before. And so another way of writing this is the coefficient of q to the n is a sum over all partitions of partitions of n with r different parts. And then here we take the multiplicities, let's say multiplicity 1 to the k1 up to multiplicity r to the kr, and divide by this factor. Okay, so I hope everything is clear now, except for this factor. So you might ask, why do you want to include this factor? I mean, this we could also put in front, or we could just leave it out. But this normalization factor has a reason. And the reason is that these Q series gk1 to kr, which can be defined in the purely combinatorial way, have a connection, a direct connection to multiple zeta values, namely that they are Q analogs of multiple zeta values, by which we mean that if I have numbers k1 up to kr satisfying this convergence condition for multiple zeta values, then I can take this Q series gk1 up to kr and multiply it with this factor 1 minus q to the k1 up to kr and send q to 1. And what I get back is the corresponding multiple zeta values. And this here explains these factors, because if I wouldn't divide out these factorials, then they would dance around here in front of this zeta value. Okay, so these multiple g's are Q analogs of multiple zeta values, but they will also be now the building blocks of the Fourier expansion of multiple Eisenstein series, because the statement is the following. So for the case r equals 2, this was shown by this paper by Gangelkani-Gonzagi. And then for arbitrary depths in my master thesis, that the Fourier expansion of multiple Eisenstein series have a constant term given by the corresponding multiple zeta values. And the rest can be written down explicitly. These coefficients a, n are given by some multiple zeta values, and where we also allow some powers of 2 pi I. And we can write this whole thing as a z 2 pi I linear combination of these multiple g's I defined before. So I think this becomes clear in an example. So in depth 1, this is clear because we just had this factor minus 2 pi I k and then this divisor sum here. But it gets interesting in depth 2. So for example, G32, and this here should be a tau, it has a constant term zeta 3, 2. And at the end here, I have the corresponding G32 with some power of pi. And in the middle, I have a mix of zeta values of depth 1 and these G of depth 1. So for example, here I have 3 times zeta 3, some power of pi, and this G2, where this power of pi always correspond to the corresponding G. And here, for example, I have 2 times zeta 2 and something with G3. And everything here can be done explicitly. Okay. And now let's go back again to the beginning. We had this example of the relation among multiple zeta values. And we saw that we get this double shuffle relation. And these are multiple zeta values are constant terms of these multiple Eisenstein series. So we could ask the same question: if I multiply 2 multiple Eisenstein series, do I get the same relation? Because the relation is satisfied by the constant term. And so this is a really naive question, but there are some problems, of course, because the trivial problem is that this question doesn't make sense because the corresponding Eisenstein series of zeta 4, 1 is not defined, because for the definition of multiple Eisenstein series, all indices had to be greater or equal to 2 at least. And so therefore, we can modify this question a little bit and ask, is there a nice extension of the definition of multiple Eisenstein series such that they satisfy these relations? And there are several works on this. So the first, again, by Gangenkanick and Sagi, they showed that one can extend the definition of these double Eisenstein series for all indices greater or equal to 1, such that they almost satisfy the double shuffle relations. So if this term here wouldn't be there, then this formula would be exactly the same as before for the zeta values. But we see here we have some derivative of Eisenstein series, which we don't see if we just look at the constant term. So they showed that this can be done for this double Eisenstein series. And then there's also a slight modification of this here by Kaneko, which doesn't involve this term, but then this formula just holds for admissible indices. And there's also an extension for which we call the shuffle regularized multiple Eisenstein series, which basically always satisfy this shuffle product in all depths. And also for some certain cases, they satisfy the harmonic product. And also the other way around, there's a definition of multiple Eisenstein series which satisfy always the harmonic product, but just sometimes the shuffle product. But anyway, none of these versions satisfy the full double shuffle relations, which we also do not expect, because we always have some derivative flying around in the room. So it's like you have a carpet which is too big for a room, and each corner corresponds to certain properties. For example, one corner is shuffle product, one corner is the harmonic product, and I can fit the carpet in the room in one corner, but then in the other corner, I still have the derivative. And for example, in this version here, the derivative is inside the product. So the statement is, I don't really have that the product equals these sides. But in these other versions, this error term, for example, is here at the shuffle product or here at the harmonic product. And but now it also makes sense that, of course, these Eisenstein series satisfy less relations, because one can show the following, which is almost by Gangenkanick and Sagi. The statement is a little bit different in the paper, but with some work, one can show that there exists an explicit basis of the space of Cusp form in each weight k, which is given by an explicit linear combination of G odd odd. So every Cusp form I can write as a linear combination of these double Eisenstein series where both entries are odd. And therefore, if I look at the constant term, Cusp forms have no constant terms. Therefore, I get a linear combination of zeta odd odds. So therefore, as a corollary, we get for each Cusp form a relation among zeta odd odds. So for example, this delta function can be written as this linear combination of double Eisenstein series. and this is a basis in weight 12. And the constant term gives this relation here. And conjecturally, these are the only relations among these zeta odd odds, where by zeta odd odds, I mean zetas of this shape here. And this exactly explains this factor in the Broadhurst-Kreimer conjecture, because this term OX times OX counts the number of possible zeta odd odds, and this minus SX counts the number of relations we get from this corollary here. Okay, so this is one explanation why these multiple Eisenstein series do not satisfy the same relations as multiple zeta waves. So this is something we expect. But of course, the natural question is, what relations do they satisfy? Can we somehow understand the relations which are satisfied by them? And if we look at this picture here again and think about this carpet, which is always too big for the room because there are always these derivatives. So if we want to describe these new relations, we also need to take derivatives into account. And maybe if we, so we could say maybe we include derivatives of Eisenstein series, but then one also sees that one also needs to include the second derivative, because if I multiply two Eisenstein series of the second derivatives, I will get the third derivative and so on. So the question is, what relations are satisfied by multiple Eisenstein series, and how can we formalize these relations? And what I mean by this is that I want to write down equations which are satisfied by these multiple Eisenstein series, but in a purely algebraic way. So, and this I first want to make clear in the case of zeta values. So let's consider the generating series of multiple zeta values, where this star here means that I consider the harmonic regularized multiple zeta values, which just means that I can make sense of these numbers for all indices such that they satisfy the harmonic product. And then these extended double shuffle relations can be written down in terms of the generating series like this. So here the first part, you can check that this exactly corresponds to the harmonic product, and the second part to the shuffle product. And here is some extra term which comes from the fact that that the harmonic regularized multiple zeta waves do not exactly satisfy the shuffle product, but one can compare them to the shuffle regularized multiple zeta waves, and there's an explicit description between these two, which somehow explains this factor. And so this equation here we can now formalize, and by this I mean forget everything I told you today. We can just start, well, don't forget everything, but we can just start with some Q algebra A. And now I just consider some formal power series with coefficients in this Q algebra A. And such a collection of formal power series will be called a mould. So this also appeared, this word appeared in the last talk of Komiyama. And now I can just ask the question, or I can define that I say that such a mould satisfies the double shuffle relation if these functional equations are satisfied by these power series. And in depth 2, I exactly mean that these equations I wrote down before are satisfied, but these relations can be written down in arbitrary depths. And then I can ask, what are the solutions? What are possible values for these coefficients? So for different Q algebras, what are possible values for these coefficients such that these equations are satisfied? And now recall, so what you forgot, namely, for example, for the case A equals R, I can take these harmonic regularized multiple zeta values, but there are also other solutions. For example, I can ask for rational solutions. And there are different approaches to this. So for example, up to depth 3, there are explicit rational solutions by Brown, Ekal, but also by Gangan-Kande-Gonzagi, by Tasaka, and maybe more. And for example, in depth 1, they are all given by this term here, by this Bernoulli number, which basically just means I take the Riemann zeta value and divide out the power of pi. And And in general, for arbitrary depths, we at least know that there are solutions to this equation, because, for example, it was shown by Rassini that there are rational solutions to these double shuffle equations, but it also follows by combining work of Drinfeld and Furusho. And but now to the variation of these double shuffle relations. So this here with this I wanted to show what I mean by formalize the double shuffle relations. And this I now want to do also for these new relations. And as I said, we want to take into account derivatives. And for this, what we want to introduce is a new family of variables. So we will again have variables x, like before. We had this mold. But now we will also include variables y, which in some sense can be seen as the variables for the derivative. And if I look at the constant term with respect to y, I can somehow think of these objects being the objects without, where I just take the non-derivative part. So what we're interested in are formal power series like this in two families of variables. And we also take a collection, which we now call a B-mold. And in such a B-mold we call symmetrial. So this language is due to Ekal. And yeah, so such a B-mold is called a symmetrial in depths 2, but this can also be written down in arbitrary depths, when the product of two such things in depths 1 can be written like this. So you see here, if you compare it with this formula from before, which corresponds to the harmonic product, then if you forget the y's, then this is actually the same formula. So somehow you can think of this being the analog of this harmonic product. And well, time is running. Here it's already tomorrow. So this is the analog of the harmonic product. But what is the analog of the shuffle product? And the shuffle product story in this case here will be a little bit different. So what we will define is when we call a B-mold swap invariant. And by the swap, which also appeared in the last talk, we mean the following. So if I take this B-mold here in depths R, then the swap is this here, which looks maybe scary at the beginning, but this can also be interpreted in a nice combinatorial way. And basically, it changes the x and y's and somehow includes the sums and differences. But for example, in depths 1, this just means that this B-mold is symmetric in x and y. And in depths 2, swap invariant just means this. And this can also be interpreted by using partitions in a nice way. And so this is now a linear relation. So how does this correspond to the shuffle product? And the analog for the shuffle product we now get by combining symmetrial and swap. So if I have a B-mold which is symmetrial and swap invariant, so I have this equation, swap invariant, and this symmetrial, then if I take the product of two of them, I can first apply the swap, changing x and y, then use this formula here, symmetrial, where now the y's are on top, and then I can again apply the swap, and then I will get this. And and what we get is, so this here is now the analog for the Q shuffle. And if you, again, at this line here, forget the y, then you somehow see why this corresponds to the shuffle product, because the x part is exactly the same. But here, this extra term, Z2, is now somehow hidden here in this thing here. And yeah, maybe my time is almost up, but what I want to say is that the variant we are interested in are B-molds, which are symmetrial and swap invariant. And so maybe I skip this part and this, because the statement is that we can actually find a solution for symmetrical and swap invariant, which are in depth 1, are exactly given by Eisenstein series and their derivatives. And this somehow can be seen as an analog to these rational solutions for the classical double shuffle equations, but now for these, this new problem here. And for example, this setup can be used to prove identities among modular forms or quasi-modular forms in a purely combinatorial way. For example, a symmetrical and swap invariant can be used to prove these Ramanujan differential equations, or to prove that every modular form is a polynomial in G4 and G6. And actually for this theorem, so the depth2 part is part of this project with Kühn and Mattes, and the depth3 part with Annika Burmester. And actually we have a conjectured construction for arbitrary depths for these objects. And maybe, so this is the B-mold I denoted, so I mentioned before, which is symmetrical and swap invariant. And the objects, which are now the coefficients, so in depth 1, these coefficients are basically exactly the derivatives of Eisenstein series. So the coefficient of this B-mold in depth 1, which we denote by GKD, this GKD is basically exactly the D's derivative of this GK minus D. And if we set these Y's to be 0, meaning here we put this 0, then these are in depth 2 are basically given by these double Eisenstein series. And they're also, so these are also defined in depth 3, and these somehow generalize what Gangan-Gonzagi called combinatorial double Eisenstein series, and that's why we call these combinatorial multiple Eisenstein series. And for example, the symmetricity of this B-mode just states that you have formulas like this here. So here you can think of, I have a derivative, the product of two derivatives of Eisenstein series, and these can be again written in terms of these combinatorial double Eisenstein series. And yeah, so then one can show that the space spanned by these combinatorial multiple Eisenstein series dk is closed under taking the derivative, or more precisely, this so this d tau, if you go from tau to q, corresponds up to a factor to q ddq, and on this level of these B-modes, this operator q ddq is just somehow this total differential here, where it takes the sum over all partial derivatives with respect to x and y. So in particular, these combinatorial multiple Eisenstein series are closed under taking the derivative. But more general, if I have a symmetrical B-mode, then using the sum of these partial derivatives always gives me a derivation on the space generated by the coefficients of this B-mode. But maybe this part I skip and maybe finish with this slide from the beginning. So maybe the end of this talk was a little bit fast, but I hope at least this part here was understandable, and also a little bit the part here. So we have these double shuffle relations for numbers, and these numbers have some natural functional analogs. And what we try to understand are these relations satisfied by these multiple functions. And if you consider these multiple Eisenstein series as a motivation for these relations, you see that you should include derivatives. And therefore, one starts here with molds and ends up here with B-molds, because somehow the second family of variables can be seen of as the variables for the derivatives of these objects. But yeah, maybe if you have good questions, then I can explain more details on these things. So thank you very much for your attention.